Hi folks, let's have a look at this idea then of the remainder theorem. Okay, so what we're going to have a look at is a way of getting the remainder when you do this kind of division here that we've just been having a look at this example here again. Okay, how could we find this remainder of 82 in a much quicker way? Because in some questions you're just asked to find that remainder or to interpret the remainder, especially if the remainder is equal to 0, and we'll come to that a little bit later. So what I'm going to do is I'm going to try and generalize what we've got here. Excuse me for that, pressing the wrong button there on my screen. Okay, so what we've basically got is we've got some sort of polynomial and we're dividing it by some sort of other polynomial. Now, one important thing for this remainder theorem to work is that the thing we're dividing by, like in this situation here, is a linear polynomial. Okay, so we're dividing by a polynomial by a linear polynomial. Now, as you can see down the bottom here, what we get when we do that is we get this 2x squared plus 10x plus 27. That's the quotient, and let's call that qx for quotient, since the first letter of the word quotient is q. And what we've also got is we can put the remainder over the thing that we're dividing by. Now let's do a little bit of rearrangement here. Let's get px on its own. So to do that, I'm going to take this x minus a, I'm going to multiply every part of this equation, I suppose you could call it, by x minus a. So if you do, if you multiply this by x minus a, the x minus a's would cancel, leaving px. The qx would get multiplied by x minus a. There's not a lot we can do with that except write qx times x minus a. And this fraction at the back here, if we multiply that by x minus a, the x minus a's would cancel and would be left with r. Now, what I'd like you to notice is this. If we let x equal to a, now why a? I'm choosing a. A is the value that makes this a linear thing that we divided by equal to 0. Now if you do that, if we let x equal to a, we're going to replace x throughout this expression, okay, with a. So what do we get? Well, we're going to put a into the polynomial. We're going to put a into the quotient in place of x, and in place of x here we're also going to put a. Now the remainder is just some sort of number, so we can't replace x there because it doesn't have x there. So if we look at this, let me just make this a different color for a moment. This is really important. We chose deliberately the value of x that makes this here equal to 0. So if that's 0, well, 0 times this quotient would be 0. So what we end up with is we're putting a into the polynomial. This part here, the quotient with a in it times 0, well, that's just going to be 0 every time. We're deliberately choosing the value that makes that linear term equal to 0, so this will always be 0, and then plus r. Well, 0 plus r is just r. Now this is an important result, and this is actually the remainder theorem. Let me just move my screen up a little bit. Easier for me to write on my tablet. Okay, so what this is saying is that if we want to find the remainder, what we simply need to do, if we're dividing the polynomial by this linear term, substitute into the polynomial the thing that makes this thing equal to 0, and we should get the remainder. Well, let's check that. Let's just test that and see if it works in this case here. So if we're dividing the same thing here and we're only interested in the remainder, let's check it. It's not a proof. This in fact is the proof here of the remainder theorem, but we should be seeing the remainder of 82 should come out when I substitute what makes x minus 3 equal to 0, which will be 3 of course, if I put that 3 into the polynomial. So let's do that. So we're going to have 2 times 3 to the power of 3 plus 4 times 3 to the power of 2 minus 3 times 3 plus 1. Let's see what that equals. Okay, 3 to the power of 3, that's 27. 2 times 27 is 54. 3 squared is 9. 4 9s are 36. 3 3s are 9, so minus 9 there, plus 1. Okay, what are we getting here? That's going to be 80 plus 10, that's 90. Take away 9 plus 1. 90 take away 9 is going to be 81, plus 1 is 82. Okay, and that definitely matches the remainder that we got through all this work here. Okay, so the overall conclusion that I want you to take away from this is that if we have a polynomial divided by some linear term, then the remainder can be found by putting a into the polynomial. Okay, and a is the value that makes this thing here equal to 0. And why does that work? Well, here's your proof. This is the proof here. Okay, so that is the remainder theorem. And what I'm going to do down here shortly is just do another example. Okay, alright, so we'll have a look at that, and then we'll have a look at something called the factor theorem as well.